For decades now, physicists and astrophysicists have been searching for a mysterious form of dark matter that cannot be observed directly but is necessary to explain the gravitational behavior of visible matter. So far, however, the search has been unsuccessful. Observations continue to indicate the need to introduce an additional ingredient into our models of the universe, but there is no known particle that can play the role of dark matter. Is it possible, then, that there is an alternative explanation for these observations and that it is not necessary to imagine the existence of a new type of invisible matter? Let's try to understand. If you are new here, subscribe to the channel and, above all, remember to click the bell icon to activate notifications and not miss new videos. Let's briefly review the reasons that led astrophysicists to hypothesize the existence of dark matter. The idea that there is much more matter in the universe than we can directly observe is almost a century old. It initially arose from the observation of galaxy clusters, which are groups of many galaxies bound together by gravity. In 1933, astronomer Fritz Zwicky noticed that the galaxies within the Coma cluster were moving faster than they should have if gravity were only produced by visible matter. Zwicky thus hypothesized that there was a lot of dark matter, meaning matter that could not be seen directly with telescopes. This hypothesis was not immediately accepted by most astronomers, but in the following decades, further observations showed anomalous behavior in the motion of visible matter in the universe. The most notable anomaly concerns the rotation of spiral galaxies, a particular type of galaxy that includes our Milky Way. Stars in the outer regions of spiral galaxies rotate faster around the galactic core than one would expect if the mass of the galaxy were only the visible mass. Once again, it's as if there is more gravity than what can be explained by the matter we can observe alone, which can be explained by hypothesizing that there is a lot of non-luminous, invisible mass in spiral galaxies. But what could this matter be that cannot be observed directly with telescopes? This is where things get mysterious, because dark matter cannot be the same type of matter that we and stars are made of, which is atoms. The reason is that we have measured the total mass of all the atoms in the universe very precisely, and it is much less than what is needed to explain the observations. Putting together all the best astrophysical observations of recent decades, it has been concluded that there should be 5 times more dark matter than atomic matter, which is the matter we are made of and all that we can see. Thus, dark matter cannot simply be normal matter that does not shine like a star. Moreover, dark matter cannot be composed of already known elementary particles because none of them, for one reason or another, satisfactorily explains the astrophysical observations. To explain the observations, it is necessary to hypothesize the existence of a new type of particle that interacts with the rest of the matter only through gravity and that does not emit or absorb electromagnetic radiation. The problem is that particle physicists have been searching for a candidate of this type for decades without success. Could there be an alternative explanation? In theory, yes. In 1983, physicist Mordecai Milgram published a series of papers showing that by appropriately modifying how gravity works, the anomalous rotation of spiral galaxies could be explained. Milgram's hypothesis is called MOND, which stands for Modified Newtonian Dynamics. As the name suggests, it is a modification of Newton's law of universal gravitation, but it applies only in situations very different from those we usually experience. Specifically, MOND assumes that stars in the outer regions of a spiral galaxy experience gravity that decreases with the inverse of the distance, rather than with the inverse square of the distance as in Newton's law of universal gravitation. In this way, at great distances from the galactic center, a higher rotational speed is obtained than expected, even without introducing a new type of dark matter. However, according to MOND, gravity would behave differently from usual only when producing very tiny accelerations, about 100 billion times smaller than the acceleration of an object falling under Earth's gravity. This situation only occurs at large distances from other masses, for example in the outskirts of galaxies or between galaxies in clusters, but not, for example, within the solar system or between planets. So, even if MOND were true, we could continue using standard gravity, for example to calculate planetary orbits, spacecraft trajectories, or how objects fall on Earth. Originally, MOND was formulated simply as a modification of Newtonian gravity made specifically to explain the motion of spiral galaxies. However, we know that the correct theory of gravity is not Newton's, but Einstein's general relativity. One of MOND's problems is that it would need to be integrated into general relativity in a consistent way, without altering the results of general relativity that have already been extensively tested in a wide variety of situations. Doing this integration consistently and without compromising the parts that work well is extremely complicated. In summary, the certainty at the moment is that there are many large-scale astrophysical observations that deviate from the behavior predicted by general relativity if the matter were only the ordinary matter we can see. To explain these observations, we essentially have two alternatives. Either we keep the theory of gravity unchanged but introduce a new type of matter for which we currently have no direct evidence. Or we do not hypothesize the existence of unknown matter but are forced to modify our understanding of gravity. This is the path taken by MOND. Which of these two is the correct alternative? In reality, both explanations have problems. The dark matter hypothesis has been dominant in recent decades and has many strengths. It does not force us to modify Einsteinian gravity, which has so far passed all the tests it has been subjected to and works perfectly as far as we know. Moreover, the dark matter hypothesis explains very well a large number of observations, not just one. It explains the motion of spiral galaxies, the workings of galaxy clusters, gravitational lensing, the expansion of the universe, the formation of structures in the universe, and so on. However, the dark matter hypothesis also has its problems, and the biggest one is that, despite all the efforts of experimental and particle physicists in recent decades, we currently have no laboratory evidence for a particle that matches the required characteristics. In fact, over time, things have gotten worse. In the 1980s, there were many promising theoretical candidates derived from possible modifications of the standard model of elementary particle physics, but experiments have gradually ruled out one candidate after another. Of course, there are still other possibilities, but there is somewhat less optimism than a few decades ago. However, the standard model of the universe shared by most astrophysicists is based on dark matter, and at the moment there are no strong reasons to abandon it, as it explains a large number of observations very well. For its part, MOND is not a complete theory of alternative gravity but rather an ad hoc addition to Newtonian gravity to explain only one aspect of the observations, namely the rotation of spiral galaxies. Over time, scientists have found that MOND can be adjusted to explain other cosmological and astrophysical observations, but it all feels a bit artificial. Recently, some theoretical physicists have made progress in developing more complete alternative gravity theories based on a generalization of MOND, but they are not theories ready to seriously compete with general relativity. It's as if the dark matter hypothesis is a good explanation but currently lacks the main ingredient, the dark matter particle, while MOND is a hypothesis that fixes something specific but struggles to explain other observations. However, it's worth noting that both of these approaches are trying to solve the same problems, and it's not ruled out that some brilliant idea in the future might lead us to a synthesis between the two viewpoints, possibly revealing the true nature of dark matter or showing that gravity works differently than we believe. What do you think? Does dark matter exist, or is it necessary to modify the theory of gravity? Write it in the comments. If you like these topics, don't forget to leave a like, share the video, and subscribe to the channel so you don't miss the next videos.